Welcome back, class. We've talked about how data routes across the world, but today we are getting physical. We are looking at the lifelines of technology, specifically focusing on connecting the IT ecosystem. Every single piece of data you interact with relies on a physical cable or interface to get where it's going, and today you're going to learn exactly what those lifelines are. To keep this organized, we are going to travel along the spatial arc. We'll start deep inside the chassis with our internal storage, managing high-speed NVMe SSDs and SATA RAID arrays. Then, we'll translate data to vision using video interfaces like HDMI 2.1 and DisplayPort. Next, we step outside the box to peripheral bridges, connecting the user via USB 4, PCIe, and Bluetooth. Finally, we will connect to the global grid using 10 GB Ethernet, Wi-Fi 7, and fiber optics. Let's dive deep inside the chassis. This is where it all begins. We are looking at the raw power and data interfaces sitting right at the core of the machine. In the realm of internal power and data, you will encounter two main standards. First is the legacy standard, Molex. This is a 4-pin power connector utilizing a red 5-volt wire, a yellow 12-volt wire, and black ground wires to power older internal drives. The modern standard taking over is SATA. SATA splits the duties, a 7-pin L-shaped key for high-speed data, and a separate 15-pin connector for power that includes a 3.3-volt orange wire. SATA is used for your HDDs, SSDs, and optical drives, but be aware of its physical limit. SATA cables have a maximum length of 1 meter. What if you want those blazing fast SATA speeds, but your hard drive is sitting on your desk? We breach the case using eSATA, which stands for External Serial Advanced Technology Attachment. This brings native SATA speeds directly to external storage enclosures. The key physical difference to remember for the exam is that the eSATA connector is straight and rectangular. It completely lacks the internal L-shaped key found on internal SATA cables. Now that our data is moving, we need to see it. It's time to bridge the gap between the graphics processing unit and the display. We start with the analog and early digital era. The classic standard is VGA, the Video Graphics Array. This uses a 15-pin D sub connector, typically colored blue, and it transmits an analog video signal only. Next came DVI, or the Digital Visual Interface. DVI is tricky because it has multiple versions. DVI-A handles analog only, while DVI-D is strictly digital. To support higher resolutions, DVI utilizes both single-link and dual-link configurations. Today, we live in the high-definition multimedia era. HDMI is everywhere, capable of transmitting high-definition digital video and audio simultaneously. Newer HDMI versions easily support 4K resolution, high refresh rates, and HDR. But for raw computing power, professionals lean toward DisplayPort. DisplayPort delivers superior performance for high-resolution computing and features multi-stream transport, or MST, which allows you to daisy-chain multiple external displays from just one single port. Let's move out of the case and connect the user to the machine using our universal bridges. Before USB took over the world, we had legacy serial communications like the DB9 or RS-232 connector. This is a 9-pin D subminiature plug that transmits data very slowly, up to 115 kbps, by sending it 1 bit at a time over a single wire. While obsolete for consumer peripherals, you will still use DB9 cables constantly as an IT tech to connect to the console ports of enterprise network equipment like switches and routers. Enter the Universal Serial Bus, connecting peripherals, power, and data. USB 2.0 supports cable lengths up to 5 meters and comes in various shapes. The flat, rectangular Type A for the host, the square, beveled Type B for printers, and mini or micro shapes for smaller devices. USB 3.0 brought super speed to the table. You can easily spot a USB 3.0 port by its blue connector tabs or housing. USB 3.0 updated the Type A, Type B, and Micro B shapes by adding additional signaling pins to handle the faster data rates. The modern superhighway is dominated by USB-C. USB-C is a compact, highly durable, and completely reversible connector. It is incredibly versatile, carrying data, video, and high wattage power all at once. This versatility is why it was adopted for Thunderbolt. While early Thunderbolt 1 and 2 used the mini DisplayPort interface pushing 20 GBps, Thunderbolt 3 and 4 adopted the USB-C physical interface to blast data at up to 40 GBps. You can identify a true Thunderbolt port by looking for its signature lightning bolt icon. In the mobile space, you'll encounter Apple's Lightning connector. This is a proprietary, reversible connector for Apple devices that requires an adapter to interface with a standard PC's USB port. Speaking of adapters, you need to know the difference between passive and active translators. A passive adapter merely changes the physical shape of the connector, like turning a USB-C plug into a USB-A plug. An active adapter, however, has internal circuitry required to actually convert signal protocols, like translating a modern digital HDMI signal into an old analog VGA signal. Now, we plug the machine into the wall and connect to the global grid. This is the massive infrastructure that spans the globe. Our foundation is copper infrastructure, specifically twisted pair cabling. UTP, or unshielded twisted pair, is the standard for almost all basic office networks. If you are running cables through heavy machinery or areas with high electromagnetic interference, you upgrade to STP, or shielded twisted pair. Pay close attention to environmental ratings. Plenum-rated cables have a fire retardant jacket required for drop ceilings and HVAC spaces. Direct burial cables are weatherproofed and armored for underground outdoor runs. To cap those cables, we need termination and standards. Our main connectors are the 8-pin RJ45 for Ethernet, the smaller RJ11 for telephone and DSL lines, and punch-down blocks using insulation displacement connectors for permanent wall links. When crimping an RJ45, you must follow the T568A or T568B wiring standards, which dictate the exact color code order of the 8 internal wires. For the exam, remember that T568A begins with white-green, while T568B begins with white-orange. For broadband and telecom, we rely heavily on coaxial cable. Coax is designed with a central copper core surrounded by thick insulation and a braided metal shield to prevent interference. It typically terminates with a threaded screw-on F-type connector. You'll see coaxial cabling used everywhere for cable modems, CATV, and hybrid fiber coax networks. Finally, we ditch the copper entirely for optical cabling, transmitting light over glass. Multimode fiber, or MMF, uses a larger core of 50 or 62.5 microns. It uses LEDs or VCSELs as a light source and is ideal for shorter distances like local area networks. Single-mode fiber, or SMF, uses an ultra-fine 8 to 10 micron core. It utilizes a highly coherent laser to shoot light across incredibly long distances, making it the backbone of wide-area networks. When terminating fiber, you will encounter 3 main connector types. The ST, or straight tip, uses a push-and-twist bayonet-style mechanism. The SC, or subscriber connector, uses a square push-pull latching mechanism. The LC, or lucent connector, is a small form factor connector that clicks into place with a retaining tab, very similar to how an RJ45 Ethernet cable works. And there you have it, the connected ecosystem. We've traced the data pathway from the spinning drives deep inside the chassis all the way out to the global fiber grid. Knowing these lifelines inside and out is exactly what makes you a capable CompTIA A+ technician. Great job today, and I'll see you in the XP Boost Labs.